Hello everybody, in this lecture we will be solving 2001 USAMO problem number 2. Here's a view of this problem. It is a geometry problem. We are given a triangle ABC and its incircle W. We will denote by D1, E1 and F1 for the touch points of this incircle with the side lengths, with the sides of this triangle, and we will denote D2 and E2 as the points on the sides BC and AC such that CD2 is equal to BD1, and similarly so let me start with that. So BD1 is this distance here, so CD2 will be probably somewhere here with the same distance, so this distance is equal to that one, so this is CD2, and furthermore CE2 is equal to AE1, so AE1 is this guy, and so probably this guy here, or maybe a bit more to this side, and that point is E2. And now the P is the intersection of AD2, so we can go ahead and connect those points. So we would like to draw AD2 like that probably, and BE2 probably like that. This point here is P according to the description of the problem, and we are told that the circle omega will intersect AD2 at 2 points. Obviously these are the points. This point is apparently called as Q, and the other point has no name, so this point, sorry for that, that has no name, and we need to show that AQ, so show that this thing is the case, so we need to prove this statement AQ is equal to D2P. This is a very well-known configuration, namely that the location of Q is by the diameter of the incircle lemma, popularized by Yufei Zhao. It turns out that D1Q is the diameter of the incircle, right? And the reason is that because BD1, this distance, is equal to D2C, the line AD2 will contain the point opposite to D1 on the same diameter. By the same reasoning, it turns out BE2 will pass through this point opposite E1. I don't know, so we can call it anything, I guess, Q prime maybe. Okay, so something like that, but that's a beautiful thing, and you can do the same reasoning for the other F1 and its opposite part as well. But okay, so let's keep it here. So this is a very well-known configuration here. This is the point I, so we're talking about all these diameters. So what do we do next? Oh, okay, so an important observation is that D2 is the touch point of the AX circle, which happens to be on the other side of BC, and similarly E2 is the touch point of the BX circle. In fact, this is the description, so P as such is what we call as the Nagel point. So you can easily check on Wikipedia or on Google for a formal description, but basically that's if E2 and D2 are defined the way they are in the problem, CD2 is equal to BD1 and CE2 is equal to AE1, what this tells me is that the intersection of BE2 and AD2, which is the point P, happens to be the Nagel point of this triangle. But then it is again a very well-known result that the line IP, so this line here, contains a special point, namely the point, namely the centroid of our triangle. So in fact, the way to identify its exact location, I can find the midpoint here. I claim that this distance is equal to this distance. D1m is equal to md2. Why? Because we know bm is equal to mc, because m is the midpoint of bc. But because bd1 is equal to d2c, it must be the case that d1m is equal to md2 as well. So finally, if I extend line am, yeah, that's not reasonable. So something like this I should do. So probably somewhere here. Let me also delete some portion of this green line here. So this is redundant. This one. Sorry for that. Okay, the reason I'm doing that is because, again, it is well known that, yeah, it is well known that the centroid here, G, is the center of a dilation, so a homothety centered at point G with a ratio -2. So this dilation will take the point M. That one is obvious, right? It will take it to the point A, because we know that G trisects the median AM. AM is the median. But furthermore, it will also take the point I, and it will carry it to the point P. As a result, this dilation will take IM to a parallel line, PA, line segment, I should say, PA. So what I'm saying is that the dilation will carry IM to AP. And obviously, because of the properties of the dilation, IM is also parallel to PA as well. And second, so this is the first important. And second of all, PA is 2 times IM because of the ratio of the dilation. Okay, so I think that's all that I need to prove the final result. And the reason is the following. Consider another dilation, namely the dilation, so let me just move this a little bit down. Consider the dilation centered in point D1. And I claim that this dilation centered at D1, which takes I to Q, will also take, sorry for that. So let me, so the dilation centered at D1, which takes I to Q, will have a ratio with ratio 2, but plus 2 obviously this time. Will also take the point M to the point D2. So this is again obvious because D1M is equal to MD2. And finally, it will, as a result, take the line segment IM, and it will map it to QD2, right? So QD2, so we are combining these two like we did earlier, so QD2. But then this implies that IM is in fact parallel to PA, or QD2, I should say. So this implies two results like previously. IM is parallel to QD2, and second of all, QD2 is equal to 2 times IM. Now, so this is result 3 and 4, you might say. Now we know very well that IM is parallel to PA, but PA is the same thing as QD2, right? They are the same line. So number 1 and 3 are basically identical results. But what's interesting is PA is equal to 2IM, but 2IM is also equal to QD2. As a result, let me continue writing on the left side here. PA is equal to QD2. Now, this implies that if I split PA, I can write it as PQ plus QA. In a similar way, I will split QD2 as QP plus PD2. Notice that PQs are common. As a result, we have that QA is equal to PD2, which is the desired result. Okay, so that solves our problem. I understand a lot of people got confused at the beginning of the problem where I claimed that G is the center of the, well, the second dilation is obvious, obviously, because we have two similar triangles. I is the midpoint of the diameter and M is the midpoint of D1, D2. So obviously triangle IDM, this is a right triangle. IDM is similar to QD1, ID1M is similar to QD1, D2, and as a result, so things are obvious. But the first dilation maybe lost quite a few of you guys, so let me elaborate on that very quickly here as a lemma, if you will. So what I'm claiming is the following. So if you focus on this triangle ABC, okay, so let's do some action here. Right, so we have the incircle, something like that, a very hairy incircle with lots of hair. Okay, oh my god, that's a monster. Okay, so you guys get the idea. Okay, good. Then we have the X circles as well. So you know where the center of the X circle would be. So probably on the intersection of this guy and the angle bisector, which will go through the center of that point. So somewhere here. So what I'm claiming is that if I drop a couple of perpendiculars here and maybe here, probably a little bit to the right, yeah, so something like that. So I should probably erase this part. Okay, so therefore, and well, okay, one more. Okay, here, so we have a circle here, right? So quickly, okay, so it's tangent here. Come on. Okay, so like that. Okay, so this is the if this is A, B, C, so this is the BX circle, right? So what the claim is that this thing is equal to this thing, and it's a very well-known result, right? So if you call this point as E here, and you call this one as this touch point here as E prime, so it's very well known that AE is equal to E prime C. Now, in a similar way, you can construct, if you call this one was B, so BD, so on this side you have D prime here, and similarly if this is an F, you have an F prime probably very close to F. So the claim is the following: the Nagel point is the intersection, of these three lines, which are actually collinear. Okay, so this intersection point, usually we call them as, so this is the Nagel point. Now, so why is there a dilation, a homothety between the in-center and this weird point and A, right? So that's something that I would like to explore on. And by the way, the Nagel point should not be confused with the Jargon point, right? So Jargon point is another point. So let me also, while I'm already onto this picture, so it is the intersection of these 3 points. This guy, this guy, so this is not necessarily a common point there. And where's the last one? Yeah, this one here. So these 3 points, these 3 lines actually concur. But anyhow, so going back to our story, why is I and NA in dilation with a center G? So what I claim therefore is that G trisects I and A, so this distance. So this is kind of a strange property because we know that G, the centroid, also trisect OH, right? The distance between the circumcenter and the orthocenter. So let's quickly prove that result. So you have, oh shoot, I should have drawn the circle first. Gosh, okay, so there you go. So for those of you, if you already know that result, so you can just skip that part, this part, so you can just continue to watch some other lectures. But I think this is a very interesting result, so that's why it warrants a proof. So the lemma is that so IG is equal to 1/2 G NA, or NA. So NA is the Nagel point, right? So let's go to our configuration here. So let's call this point as D, this point is E. AE is equal to, let's call this point as E prime here, and BD is equal to, let's call this one as D prime. So let's figure the following. So we have this line here, BE prime and AD prime. Okay, so because of the lemma, the very well-known lemma, that the diameter of the incircle lemma, we know that AD prime will go through the point opposite D, and in a similar way, we know that we know what? Yeah, we know that the BE prime will go through the diameter opposite, so the point E, the point opposite point E on the diameter, right? So this point is, actually, let me not name these points, or okay, let me just call this one is E double prime and this guy is D double prime. But notice that this point here is the in center, right? So now, so yeah, so this is a single, so this distance here is equal to that distance. So now we are up to something. So the midpoint here is M. M is the midpoint of not only BC but also DD prime, because this BD is equal to D prime C. So now I will go ahead and draw my the median from A to come on. Okay, so this is the median now, and focus on this point. So this point is, we decided to call it the Nagel point for now. Well, okay, so it's any point. Okay, forget about the Nagel, the name. Come on, just get rid of it. Okay, so what I need to show is that there exists a dilation where G will take, G will do some stuff. Okay, so where is G located? So G is on AM, but moreover, say that G is somewhere here. I don't know where G is exactly, so let's say it is anywhere. Okay, so the centroid is the center of a dilation with ratio of -2. Before I do that though, let me just remind you one thing. I am here, I am is the midline of triangle D double prime D D prime. I am is midline of triangle D double prime D D prime, and the reason being that I is obviously the midpoint of the diameter DD double prime, and M is, we already clarified that it's the midpoint of DD double prime. As a result, IM is also parallel, and IM is parallel to AD prime. AD double prime D prime. So this is a line. Okay, so the dilation, consider this dilation here. It will take the point M, so this one is the easy one. So HG will take the point M and it will map it to the point A, because we know G, the centroid, will trisect the median. But what's surprising is, because IM is parallel to AD prime, the dilation will map IM to a line somewhere, so it will be mapped to a subset of the line AD prime, somewhere on a range on that, so implying that the dilation will take I to a point somewhere on AD prime. So that's neat. But by the same token, but due to the symmetry, that there's nothing special about the vertex A, right? We should also get symmetrically that the dilation will also take I to the point BE prime, and also even though I didn't draw it, so it will also take it to the point CF prime. But there's only a single point which is a candidate for that, and it is the intersection of AD prime and BE prime, right? So there is no other point that it can be, right? So therefore the image of I under this homothety will be precisely this point, which I don't know, so we can now call it as the Nagel point now. And moreover, G has a special location. It is on this line connecting I and the Nagel point, and furthermore IG is equal to 2IG is equal to G and A due to the dilation, right? So the distance here is x. You can call this guy as 2x as well. But that's basically the lemma, and I hope you enjoyed it. The main problem, the USAMO 2001 problem number 2 this was, and hope to see you in our next video.